What if, somewhere in the silent darkness beyond our solar system, an invisible force was already moving toward us? Not glowing like a star, not burning like an asteroid, just silent gravity, bending space itself as it drifts through the galaxy. Imagine astronomers noticing something unusual. Distant stars slightly shifting, the outer planets behaving unpredictably, small irregularities in orbital paths that cannot be explained by known physics. At first, it would look like a minor error in calculations. Then the data would repeat, and the pattern would become impossible to ignore. The source would not shine in the sky. Telescopes would not capture a dramatic image of destruction approaching Earth. Instead, scientists would detect distortion, light bending in subtle arcs, trajectories curving in ways that defy expectation. Something massive, something unseen, something powerful enough to reshape an entire planetary system. Then the realization would emerge. A rogue black hole, a collapsed star wandering through interstellar space, carrying gravity so intense that even light cannot escape its core. Not hunting us, not targeting us, simply moving, following the silent mechanics of the universe. Could Earth actually be swallowed by one? Would we see it coming decades in advance? Would gravity slowly tear apart our orbit before we understood what was happening? Or would the end arrive in quiet inevitability, as physics calmly unfolds its most extreme consequences? Tonight, we explore this question not through fear, but through science, because the universe does not rely on imagination. It follows laws, and sometimes those laws are more dramatic than fiction. Before we imagine Earth being swallowed, we need to understand what a black hole truly is. Despite the dramatic name, it is not an empty void consuming everything nearby. It is a physical object, born from the death of a massive star. When a star far larger than our Sun exhausts its nuclear fuel, gravity overwhelms the outward pressure that once kept it stable. The core collapses inward. If the remaining mass is great enough, it compresses beyond atoms, beyond neutron matter, into something so dense that space-time itself curves inward dramatically. At the center lies what physicists call a singularity, a region where our current understanding of physics breaks down. Surrounding it is the event horizon, the boundary beyond which nothing can escape. Not light, not matter, not information, as far as we currently understand. But here is the crucial detail. From a distance, a black hole behaves like any other object with mass. If our Sun were replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does today, though without sunlight. Black holes do not suck objects from across the galaxy. The real danger comes from proximity. As an object moves closer, gravity intensifies rapidly. Tidal forces stretch matter. Orbits destabilize. Space visibly bends. So the real question is not whether black holes exist. They do. The question is whether one could ever drift close enough to disrupt the delicate gravitational balance that keeps Earth safe. And to answer that, we must follow the physics step by step. To understand whether Earth could be swallowed by a black hole, we must begin by stripping away the dramatic imagery that often surrounds these objects and focus instead on the physics that governs them. A black hole is not a cosmic predator actively hunting planets, nor is it a swirling tunnel randomly devouring everything nearby. It is the natural result of gravity pushed to its ultimate extreme. Every star exists in a constant battle between two opposing forces, gravity pulling inward and nuclear fusion pushing outward. For millions or even billions of years, this balance keeps the star stable. But when a massive star exhausts its nuclear fuel, the outward pressure weakens and gravity gains control. If the remaining core is heavy enough, nothing can stop its collapse. The matter compresses beyond atomic structure, beyond neutron density, into a region so compact that space and time themselves curve inward dramatically. This collapse forms what we call a singularity, a point where density becomes extreme and our current understanding of physics begins to break down. Surrounding this singularity is the event horizon, not a physical surface, but a boundary in space-time beyond which escape is impossible because the escape velocity exceeds the speed of light. Light itself cannot climb out of this gravitational well, which is why black holes appear black. However, from a distance, a black hole behaves just like any other object of the same mass. Its gravitational pull follows the same laws that govern the motion of planets and moons. If our sun were magically replaced by a black hole with identical mass, Earth would continue orbiting at the same distance, following the same path. The difference would not be immediate destruction, but darkness and cold. This is a critical distinction because it shows that black holes are not magical vacuum cleaners sucking in everything across the galaxy. The real danger emerges only when an object gets very close. As something approaches a black hole, the difference in gravitational pull between its near side and far side increases dramatically. These tidal forces stretch matter along the direction of gravity and compress it along other axes. On Earth, tidal forces from the moon create ocean tides. Near a black hole, those forces become so extreme that they can tear apart stars before they even cross the event horizon. This stretching effect, often called spaghettification, occurs because gravity does not pull uniformly across an extended object in such intense environments. The severity of this effect depends on the size of the black hole. Smaller stellar mass black holes produce stronger tidal forces near their event horizons, while supermassive black holes have larger horizons where tidal effects at the boundary can be less immediately destructive. There are different categories of black holes observed or theorized in the universe. Stellar mass black holes form from individual massive stars and can range from a few times the mass of the Sun to several dozen times more massive. Supermassive black holes reside at the centers of galaxies and can contain millions or even billions of solar masses. Our own galaxy hosts one at its center, located tens of thousands of light years away, posing no threat to Earth. Some scientists also theorize the existence of intermediate mass black holes and primordial black holes formed shortly after the Big Bang, though evidence for some of these remains under investigation. Most black holes are not actively feeding. They drift silently unless they interact with nearby gas, dust, or stars. When matter falls toward a black hole, it forms an accretion disk, heating up through friction and emitting intense radiation. This is often how we detect them. But a rogue black hole traveling through relatively empty interstellar space could remain almost completely invisible. The idea of Earth being swallowed would require such a rogue object to pass extraordinarily close to our solar system. Considering the vast distances between stars, the probability is extremely small, yet not physically impossible. The universe operates on scales of time and space that dwarf human intuition. Over billions of years, rare events do occur. If such an encounter were ever to happen, it would not begin with sudden annihilation. It would begin with subtle gravitational disturbances that slowly grow stronger as distance decreases. Gravity does not need to announce itself loudly. It simply reshapes motion, orbit, and eventually structure. And understanding that gradual progression is the key to answering whether Earth could truly be swallowed by one of the most extreme objects in the cosmos. As the rogue black hole moves deeper into the solar system, the balance that has governed planetary motion for billions of years begins to unravel. Gravity, once predictable and stable under the Sun's dominance, becomes a shifting equation with a new massive variable introduced into the system. The outer planets would feel the change first in dramatic ways. Their orbits, once nearly circular and stable, could stretch into elongated ellipses. Some might gain energy through gravitational interaction and be flung outward into interstellar space, becoming rogue planets themselves. Others might spiral slightly inward toward the Sun. These interactions would not be orderly. They would follow the complex mathematics of gravitational dynamics, where small differences in position lead to radically different outcomes. Jupiter, the most massive planet in our solar system, would play a crucial role. Its immense gravity could either shield the inner planets by altering the black hole's trajectory slightly or amplify the chaos by transferring orbital energy in unpredictable ways. Gravitational slingshot effects could accelerate objects to extraordinary speeds. asteroids and comets might be scattered in all directions, increasing the likelihood of impacts throughout the system. As the black hole approaches the region of the inner planets, the effects would become far more noticeable on Earth. Our orbit around the Sun might begin to deform significantly. The length of a year could change by days rather than fractions of seconds. Seasonal cycles would shift unpredictably. Climate patterns would become unstable as Earth's distance from the Sun varies more dramatically during each orbit. The Moon's orbit could also destabilize. It might drift closer, intensifying tidal forces on Earth, or move farther away, altering ocean dynamics and rotational stability. Tidal forces from the black hole itself would begin to affect Earth more directly. Unlike the gentle tides produced by the Moon, these forces would be far stronger if the black hole comes within planetary scale proximity. The side of Earth facing the black hole would experience a stronger gravitational pull than the far side. This difference in force would begin stretching the planet ever so slightly. At first, the deformation would be microscopic, measurable only through precise geophysical instruments. But as the black hole draws closer, the stretching would increase. Ocean tides could rise to extreme levels, not just along coastlines, but across entire hemispheres. Water would bulge outward toward the approaching gravitational source. Massive tidal surges could devastate coastal regions repeatedly as the Earth rotates. The crust of the planet would respond to these stresses. Tectonic activity could increase as the planet's internal structure adjusts to uneven gravitational strain. Earthquakes might become more frequent and more powerful. Volcanic systems could activate due to shifting pressure distributions within the mantle. The atmosphere itself would feel the consequences. Changes in gravity and orbital speed could alter wind patterns and global circulation systems. Weather would grow more chaotic. If the black hole's path brings it extremely close, Earth could face one of several fates. One possibility is gravitational ejection. Earth might be pulled out of its orbit around the Sun and captured into a new trajectory around the black hole, or flung entirely into deep space. In that scenario, our planet would become a rogue world, drifting without a star. Surface temperatures would plummet as sunlight disappears, freezing oceans and collapsing ecosystems. Another possibility is temporary orbital capture. Earth might begin orbiting the black hole at a certain distance, creating extreme gravitational gradients. In this configuration, time itself would begin to behave differently relative to distant observers due to relativistic effects. Clocks on Earth would tick at slightly different rates compared to clocks far away. The sky would appear distorted as starlight bends dramatically around the massive object. If the approach continues and Earth's trajectory intersects fatally with the black hole's gravitational well, tidal forces would intensify beyond survivable limits. The stretching effect known as spaghettification would begin not as an instant tearing apart, but as progressive structural failure. The planet's spherical shape would gradually distort into an elongated form aligned with the gravitational field. The side facing the black hole would accelerate more strongly than the opposite side. Mountains would fracture under uneven stress. Oceans would lift into colossal tidal bulges thousands of meters high before being torn into streams. The crust would crack, releasing energy in catastrophic seismic events. As distance continues to shrink, gravity would no longer merely deform the planet. It would overwhelm its structural integrity. Earth's self-gravity, which normally holds it together, would be insufficient to counteract the tidal gradient imposed by the black hole. At that point, fragmentation would begin. Massive sections of crust and mantle could separate, forming arcs of debris pulled into elongated trajectories. The once stable world would transition into a stream of matter spiraling toward the event horizon. Throughout this entire progression, there would be no explosive cinematic moment in the traditional sense. The destruction would be driven by relentless gravitational mathematics. No fireball from within, no cosmic roar, just gravity reshaping matter at every scale. And if Earth crosses the boundary from extreme proximity into the region beyond return, the final stage would begin. If Earth were pulled so close that escape velocity exceeds the speed required to break free, the planet would approach the most mysterious boundary in astrophysics, the event horizon. Contrary to popular imagination, there would be no visible wall, no glowing barrier marking the point of no return. The event horizon is not a surface made of matter, but a limit in space-time itself. It represents the radius at which gravity becomes so dominant that all possible paths through space and time curve inward. As Earth approaches this boundary, relativistic effects would become increasingly dramatic. To distant observers watching from far outside the black hole's influence, our planet would appear to slow down. Light escaping from Earth would lose energy as it climbs out of the deepening gravitational well, becoming stretched to longer wavelengths in a process known as gravitational redshift. The planet would gradually dim and redden, appearing to freeze at the edge of the event horizon. From their perspective, Earth would never quite cross it. Instead, it would fade, asymptotically approaching the boundary over an infinite stretch of external time. But from Earth's own perspective, time would feel normal locally. The laws of physics in the immediate environment would continue operating according to the same principles, though under increasingly extreme curvature of space-time. If the black hole is sufficiently massive, tidal forces at the event horizon itself might not yet be instantly destructive. Earth could, in theory, cross the boundary without feeling a sudden jolt at that exact moment. The true violence would intensify deeper within the gravitational well. Once inside the event horizon, all future directed paths lead toward the singularity. There is no stable orbit, no possibility of turning around. Gravity does not merely pull inward. It defines the direction of time itself toward the center. As Earth continues inward, tidal forces would escalate beyond anything experienced before. The difference in gravitational pull between the side of the planet closer to the singularity and the far side would increase exponentially. The stretching along the radial direction would become extreme. The spherical shape of Earth would distort further into an elongated structure. Oceans, already destabilized, would separate into streams of vapor and plasma. The crust would fracture completely, breaking into massive segments drawn out like beads along a string. The mantle and core would no longer maintain coherent structure. Atoms themselves would experience enormous tidal gradients. In smaller black holes, this spaghettification process would occur before reaching the event horizon. In supermassive black holes, the event horizon could be crossed before tidal forces reach their peak, but eventually the increasing curvature ensures total structural breakdown. The fragments of Earth would not fall in as a compact sphere, but as a long, glowing filament of matter spiraling inward. Friction within this elongated stream could heat material to extreme temperatures, potentially emitting radiation until the final descent progresses beyond visible detection. As the fragments approach closer to the singularity, the curvature of space-time intensifies dramatically. Our current physics cannot fully describe what happens at the singularity itself. General relativity predicts infinite density and zero volume, but quantum mechanics suggests that such infinities signal incomplete understanding. Some theories propose that information about infalling matter is preserved on the event horizon in subtle quantum states. Others suggest more exotic possibilities involving quantum gravity effects or connections to other regions of spacetime. Regardless of the deeper theoretical implications from the practical standpoint of physical structure, Earth would cease to exist as a planet long before reaching the singularity. It would be reduced to fundamental particles stretched along extreme gravitational gradients. The distinction between surface and core, ocean and atmosphere, would disappear entirely. From the outside universe, however, observers would never see Earth cross completely. They would witness a fading image, redder and dimmer over time, as signals struggle to escape the deep gravitational well. Eventually, the radiation would become too weak to detect, and Earth would effectively vanish from observable reality. The black hole itself would grow slightly in mass, incorporating the energy equivalent of our planet according to the relation between mass and energy described by relativity. Yet even that addition would be minuscule compared to the total mass of the black hole. The universe would not tremble. The galaxy would not shift noticeably. A single planet would have merged into one of the most extreme objects in existence, its structure erased, but its energy conserved in accordance with physical law. The final mystery would remain unresolved. What truly happens at the singularity? Does matter compress into an infinitely dense point, or does some deeper quantum structure prevent that outcome? Until a theory of quantum gravity is fully developed, this remains one of the greatest unanswered questions in science. But one thing is certain: crossing the event horizon marks the irreversible end of any planetary identity. Beyond that boundary, there is no stable matter, no intact structure, and no path back outward. Only gravity, space-time curvature, and the relentless pull toward a region where our understanding of reality reaches its limit. After exploring the full gravitational progression from distant disturbance to final descent beyond the event horizon, the most important question remains: how realistic is this scenario? Could Earth truly be swallowed by a black hole in the foreseeable future, or is this an extreme theoretical exercise? The honest scientific answer is that while the laws of physics allow such an event, the probability is extraordinarily small. The universe is vast beyond everyday comprehension. The average distance between stars in our region of the Milky Way is roughly 4 light-years, which is nearly 40 trillion kilometers. Black holes, especially stellar mass ones, are typically remnants of massive stars and are scattered across the galaxy with enormous separations between them. For a rogue black hole to pass directly through our solar system would require a very precise alignment of trajectories formed over millions or billions of years of galactic motion. The Milky Way itself is in constant rotation, with stars orbiting the galactic center at high velocities, yet the distances between objects remain so immense that direct close encounters are rare. Astronomical simulations suggest that while stellar flybys occur over cosmic timescales, encounters close enough to severely disrupt interplanetary systems are uncommon. Even when stars pass relatively near one another, they often do so at distances that primarily disturb outer comet clouds rather than inner planets. A black hole passing within the Oort cloud is more plausible over billions of years than one passing within Earth's orbital radius. Additionally, modern astronomy has become increasingly capable of detecting massive objects through gravitational effects long before they pose danger. Surveys continuously monitor stellar motions and gravitational lensing events. A black hole with significant mass approaching within even several light years would likely produce detectable anomalies in surrounding star trajectories. In practical terms, humanity would probably have warning centuries or longer before a truly dangerous approach, assuming detection systems remain active and technologically advanced. Another stabilizing factor is gravitational probability itself. The solar system occupies a relatively calm region of the galaxy, far from the dense stellar populations near the galactic center where interactions are more frequent. Our position in the galactic disk reduces the likelihood of close encounters compared to more crowded regions. Furthermore, most black holes are not wandering unpredictably, but orbiting the galaxy in stable trajectories similar to stars. The scenario that poses the greatest risk would involve a black hole receiving a significant gravitational kick from a supernova event, altering its path into a rogue trajectory. Even then, the chances of intersecting precisely with Earth's orbital path are incredibly small. On cosmic timescales spanning billions of years, rare events do accumulate probability. But within the lifespan of human civilization, or even the remaining lifetime of the Sun, the risk remains negligible. It is far more likely that Earth's distant future will be shaped by the Sun's natural evolution into a red giant billions of years from now rather than by a passing black hole. However, studying such extreme possibilities is not an exercise in fantasy. Black holes provide crucial laboratories for testing general relativity, quantum field theory, and the limits of gravitational physics. Observations of black hole mergers through gravitational waves have already confirmed predictions made over a century ago. By understanding how extreme gravity behaves, scientists refine models that apply not only to hypothetical planetary destruction, but to the fundamental structure of space-time itself. There is also a philosophical dimension to this exploration. Imagining Earth swallowed by a black hole forces us to confront the scale of the cosmos. Our planet, which feels vast and permanent from a human perspective, is a tiny gravitationally bound sphere orbiting a single star in one of hundreds of billions of galaxies. The forces capable of reshaping or destroying it are not malicious. They are simply the natural consequences of mass and curvature. In that sense, the universe is neither hostile nor protective. It is governed by consistent physical laws that operate regardless of human presence. The same gravity that could, in theory, tear apart a planet is the gravity that allows stars to shine and galaxies to form. Ultimately, while the image of Earth being swallowed by a black hole is dramatic and scientifically grounded in possibility, it remains one of the least likely threats facing our planet. Cosmic stability dominates over chaos across most of space and time. The solar system has remained dynamically stable for over 4 billion years, and current observations suggest it will continue to do so for billions more. So could Earth be swallowed by a black hole? Yes, in principle, under the unyielding laws of gravity. But in reality, the universe appears far more inclined toward long periods of equilibrium than sudden catastrophe. And perhaps that balance, fragile yet enduring, is one of the most extraordinary features of the cosmos we call home.